Hello, this is an example. It concerns with the derivative as a rate of change. I remember when I was at the preparatory that it was kind of confusing thing, this thematic, because at that moment I didn't have computer and I had to make my notes by hand and all that. But now I wanted to make this example doing the graphs and establishing the figures and the values with the functions. For instance, here I have the example is that if you have a cube and there is a formula where you can find the volume of this cube. The formula is f dx equal x to the third power, and as we can see here, x is this is every side of that cube that is always the same, but the function is saying that x multiplied by x and then multiplied by x, and this is why we have y equal x to the third power. So we can calculate with this sheet of Excel and with Excel, and then just set up the numbers here. For instance, the range here was 5 to 4, but the idea about the derivative is, for instance, we have, if we want to compare the change of the volume of this function that we have here in this formula, when x is equal 4, we have, for this value 4, we have 64 is the value of the function. But if we have that we can increase a little value in y, we have to change a little value here in x, that is called delta x. This is x plus the little change that we can say there is infinitesimal change, and we add to the 4, and then we calculate all this expression to the third power, and then minus 4 minus the initial value that we have. The initial volume when x is equal 4 minus the final value of 4 delta x to the third power. And what we have here is the rate of change, the volume that was increased from x to delta x, and we can calculate this doing the derivative. For instance, delta y divided by delta x equal x to the third power, and then this expression is the same as we have the derivative y respect to the derivative of x, and if we derive this, we have the next expression, that is 3x square. That is this next column of dates, and we can graph all this information here. Here's the graph. But the most important thing here is that when we evaluate the infinitesimal increasing of this number, we can see that the rate of change is 48. This means that when we have 4 in this side of x, we have a volume of 64. This is the volume, and this function here is the those figures are the derivatives, and the important here is that the derivative when a small increasing of x, that is small, that can be small until the infinite, we have a relation that is for every figure here. For instance, if we separate from this figure and we separate just this infinitesimal part, the derivative is saying that the rate of change of this small number is changing 48 times, as we can see here that it is the same here. if we have 4 and 100th, and if we can separate 4 and just take it this 100th, we can say that at that moment can you see the volume here? The volume here is 64.48 hundredths, and the derivative at that point is 48 as well, and in all the figures that we have here, all there are almost no changes, right? Because we can have this small change here, and we can have a little more and more smallest number that we could think, but the rate of change is saying that when there is a small quantity, for instance here, the rate of change is 48 times this number, as for instance here 4 and 1,000th, we can see a little increment increasing of 1,000th, but we can say here that this increasing was 48 thousandths, and is always is the same, you know, in all those in this approaching, because this is tending to 0. We can see that this is tending to 0, and is the is the same number in every figure, that every small change that you have in the with x and the volume is the same, and we have this is the function of the derivative, and we can see the graph here. For instance, this is the graph for this is this blue is the volume, and the red is the graph of the derivatives. that actually is this. This is a much more broader graph, and in another scale, but it's the same.